introduction, I want to just basically present two distinct papers that we have published in 2015 that use multimodal machine learning for some tasks, and they should just be kind of like explanatory or examples of like how you can use the methods that we discussed on Monday. In this work, this is a collaboration with one of my summer interns in 2015, Martin Brielman. He's from the University of Twente in the Netherlands, and he kind of wanted to get his master thesis done on predicting who's going to win a debate. And so we basically wanted to find out what multiple behaviors predict the debate outcomes. And in this case, we were interested in finding out which team is going to win. So we have kind of like multiple levels of analysis. On the one side, we want to know which speaker is performing well, and we want to know which team, so there's always teams of two against each other, and then in the overall assessment of the debate, which team is going to win. So that thought came from the fact that in a team there might be a good and a bad speaker, and together they will lose. But if you have two very good speakers in the opposing team and two mediocre, good, or like well prepared speakers, you would have a difference in the performance there as well. All right. So let's look into this. The goals, first of all, was to create a novel debate on giving presentations or like doing debates. We want to find relevant nonverbal features and predict who's going to win the debate. We have this data set available, and we would like to also remind you that we could share that. We've expanded it quite a bit. The work is still continuing, and we're expanding our analysis into, like, for example, what makes a good verbal argument. Right, let's delve into it. So the motivation is clear. We want to identify what kind of performances and what kind of behaviors give away good performances in public speaking. So what is the gesture, the gestures that the person has to do? How does the voice have to sound like? What is the pace of the voice? The intensity and potentially even the structure of the argument. And this research is work that we developed within the CISRO project, which is the public speaking project that Mathieu and myself have talked about previously, so that you kind of know where this falls into the context. And we are interested in this case not in public speaking, but more in the debate domain, that you could imagine use this also to identify who is going to win the presidential debates and who has the better arguments. Okay, so the debate database consists of 30 Oxford-style debates. That means that you have a proposition. For example, one proposition is we have to ban college football because of all the head injuries. That would be a proposition. And then you have two teams, one for the proposition and one against it. And they give an opening statement that is 6 to 7 minutes in length. And each speaker in turn gets to speak about their opinion and how it relates to the proposition. Then there is a 45-minute, on average, kind of open question kind of phase where the audience can ask questions, the moderator can ask questions, and the debaters can address each other directly. That open question round is followed by a closing statement, which is 2 minutes in length, and basically just sums up the ideas, or kind of brings the final argument of the speaker. for our analysis, we only use the opening statements and the closing statements. And can you imagine why we did that? So we wanted to make it as easy for us as possible, and I think this is something that I've seen a couple of you guys also propose. For example, the group that's working on the stand-up comedians, they don't want to include segments where you, for example, see the audience. You only want to see segments where the speaker is actually addressing the audience directly. So we wanted to have a machine learning model that doesn't have to deal with, for example, interruptions, back channels of other people, reactions by the opposing team, and so on. So we wanted to have it as clean as possible and as consecutive as possible. So we have like 6 minutes of continuous data for one speaker in the beginning and 2 minutes at the end. So that kind of makes it easy for us to process the data. So that's just kind of like the idea about that. And also, so just so you know, these are professional speakers, and we had a skewed data set towards male speakers. This is unfortunate, but unfortunately, the website here doesn't provide us with more female speakers. That is definitely a caveat and a problem here. This is kind of like how this looks like. First of all, you have the stage overview. You have one team on the left and one team on the right side. You have no, here he is, I think. You have the debate leader, the moderator, and this guy is giving the opening statement. The opening statements are standing, and the closing statements are sitting. So you can already imagine that when we do our machine learning model, that we build a model for the separate kind of setups. So we have one model that looks at opening statements and one at closing statements, and that is just because in ascending form or in a standing position, your voice sounds differently, you gesture in a different way, the podium influences you. So there's a podium here that goes probably higher up than the table here, so the behavior of the individuals is just a bit different. So you wanted to kind of even that out over our analysis. And down here, you also see the results. So what this data set has actually as an advantage for us in the analysis is that we already get provided by sufficient labels. We know who's winning. We know how the voting was in the pre-debate section. So in the pre-debate, these guys had 65% and these guys had 14% of the support from the audience, which is about 500 people. So you would say the for the motion or for the proposition, these guys are winning because they have 65% of the support. But this is not how Oxford-style debating works. The actual winner of the debate is not defined by who gets the most votes, but who changes the opinion the most. So these guys changed the opinion from pre to post by 0%. But these guys doubled their percentage. They gained 14%. So actually the against vote wins this debate because they have changed the most opinions. And the proposition or the motion in this case was the GOP must seize the center or die. Just for information, like here's the vote before the debate and here's the vote after the debate. Okay, other questions about this? So like this is kind of like the train of thought that I would like to see in your own project, so that you identify what the data set, what constraints you have, where do you get your labels from, and what the data looks like, so that you can extract the best. Yeah.
So can the speaker just perform really bad in the pre and perform very good in the post, and then people will change?
Yeah. So the vote pre is before they have seen anything.
Oh.
The moderator comes out and says, "This is our motion. These are the facts. Vote now." And then he brings in the speakers, and then they introduce themselves. And then they do the opening statement, the opening questions, the closing statement, and after this is done, the speakers sit down and the moderator says, okay, now vote again, how have you changed? So they vote before they've seen any speaker.
How do you evaluate the individual speakers if the votes are on team basis?
That's a good question. So we don't know how well or how bad they speak personally or like as an individual, but we take the same label as for the team for the individual. Yeah, that's just also a little problem there. Cool. All right. So the other interesting thing about this database is that it has a very large range of topics. So they talk about different things all the time. So sports, politics, social questions, medicine, etc. So this is very, very, very interesting. They talk about vaccinations and like whatnot. So it's very, very cool data set. It's also expandable. We already expanded it. I think we have, this was on 30, we have like 50 now. So this is a really cool data set that's just growing. And all the videos are on YouTube and you can download them. Yeah, it's very, very nice. The winner is known, people vote on it. We have a fixed debate format, so that doesn't change either. We have the 6 minutes of opening statements and closing statements. And the video is high quality. And the cool thing also is that transcripts are available, so you can actually also look at text, but we haven't done that in this study. So we extract audio features. You might have seen this already, so we use cover-up features. And what we were interested in was looking at voiced, unvoiced. This first column that you've seen in the homework, or is it the second column? I think it's the second column. Where this one is 0 or 1 all the time, and you can imagine that we use this. So the 0 means that we don't have voicing. That is the case when we have like fricatives or plosives or closing like closures in the mouth as tones, but also when the person's not speaking, right? And so we want to kind of know what's the relationship or the ratio between like the person speaking and not speaking. So we use this as a proxy of like speaking rate and these kind of measures. So that's kind of cool. We look at pitch. We found in previous work that, for example, like a deep voice with a low pitch in political speeches has an impact on the audience. So male speakers are at an advantage there. Yeah, the performance, basically like the expressivity, how flat, how monotonous, or how much the voice goes up and down. And then we also look at voice quality. And here, there's actually a couple of interesting things about voice quality where you have individuals with a very tense voice and they're male, they're perceived as dominant speakers or persuasive speakers, but female voices not necessarily are perceived as positive if they're tense than when as in comparison to male speakers. So there are like gender differences too, but since our data set is so skewed, we kind of ignored those, but this is something to keep in mind for yourself. So it often makes a lot of sense to model male and female speakers separately, or just users in general separately. Okay, for video features, we use gaze, head motion, and smiling features, and a couple of facial expressions like happy, sad, etc. Serious or angry. Like so we kind of approximate these more debate-related or relevant facial expressions like sincerity through facial expressions that we get provided through the facet framework. And you have seen those features as well in your homework. Yeah, so these are kind of like the features and facial expressions that we're looking at. Okay. So on the verbal domain, we were also thinking, okay, so we have the text. We don't necessarily know when the person says what exactly, because we only have like annotations on like a couple of second bases. So we know the sentence happens within second so-and-so and second so-and-so. And so we only have like a rough estimate of like when the person has said the following sentence. So we tried to come up with a way to kind of synchronize the facial expressions, the audio that come in at real time, at a frame basis, with the text that comes in at this a lot wider time segment that we cannot like precisely define. And so what we did is we used the loop features that Mathieu talked about, where we looked at pronouns, so how many times or how often does the person say I versus us, like maybe kind of create a relationship with the audience. Does the person incite like a feeling of importance in the listeners, so that they can persuade the audience better? How is it about like positive versus negative emotions? Is it better if you're, for example, for emotion and you create positive emotions because you want to create like a positive link to what the preposition is, or is it better if you have a negative emotions where you kind of talk about what negatively would happen, or what would happen if you would ignore the proposition and you would start to move into a different direction. So it's kind of like trying to find out on a very like 30,000 feet up kind of level what emotion and what kind of words would change the opinion. So that's that kind of idea there. Right. And then a couple of things that we found. We found, for example, that there's a larger pitch range where you have a wide range of fundamental frequencies, which means basically that the individuals are more expressive, and that is found in the winners. We found that they exhibit less breathy voices, so they are more tense in their voices, which is also what I just mentioned before. And I think this is the case mainly because we have a huge gender bias towards male speakers. I think if that was more equally split, and we would then look at it for both male and female speakers together, there might be a difference here. We might lose this significance here, but then if we would model it separately again, we might get it again. And they show less joy, which is interesting. So they are more sincere in a sense, and they are more expressive with their head movement. Yeah.
How do you model joy using the audio or words?
No, this is from facial expressions. Yeah.
Just a smile level.
Yeah, so we have kind of three modes to get at that. So we have AU6, which is like these wrinkles here. So the lip raiser, the cheek raiser, and we have the smile, like the mouth corners go up. So these are AU6 and AU12. And then we have also a full facial analysis model through the Facet software, which just gives you an estimate of, oh, this is happy. Right. And so it's kind of like a compound measure. And you can see all these, the exact things that go on in that paper if you look at that. We found also that there are large differences between opening and closing statements in this data set. So this is also because I mentioned that in one case they're standing versus the other case they're sitting. Okay. For machine learning experiments, we did the following. So we created 8 support vector machines in the first run, where we have so we have the features come in that are co-overlapped. We build one for closing statements, one for opening statements. For Facet, opening statements, closing statements. Cow, opening statements, closing statements, and so on. And then, so what kind of method is that? Lake fusion, exactly. And so then we kind of create a decision fusion at the end here, which is on a person basis. So for each person, we get an estimate of like, is the person a winner or a loser, based off of 8 different outputs, and we can just either do majority vote or max or whatever, and I think we just did majority vote. And so we have one fusion for each person. It comes out here as an arrow, and we have 4 debaters, and they come in And we ordered always, so this is also important for this model, obviously, that you always want to have the for and against on one side, right? And then we basically created a debate fusion also on a majority basis, so who is winning, who is losing. And then we had a debate result. We can also just do a team results where you would say you combine the estimates for each team and then get it like the performance per team as well. So if we wanted to kind of maybe learn a model here, what would we have to do? What kind of difference is like? So we could just like change this simple majority vote fusion into like a classifier, like a support vector machine or something like that. What are the steps that we need to do here? So the most trivial one, I guess, is like we shouldn't do that on the same data set as before. Okay, so we need a bit more of like a larger data set, or we would have to hold out different sets of data. But then also, I think we wouldn't want to have zeros and ones here. We wouldn't want to have just like the final decision coming out of this model. I think what would be great is if we would have maybe like all the information come in, like all the decisions from the support vector machines get into this model. We could also imagine that we would maybe want to, in this case here, model two speakers against each other. And so we have like one feature vector that pertains to one speaker versus the other feature vector that pertains to the other speaker, and see like, okay, who's winning, left or right, or something like that. So that would be an option, but you also could just subtract the feature vectors from each other and say, okay, who wins, left or right. And so there are many options to kind of combine and to relate speakers towards each other. And we're kind of exploring some of those things with a large data set right now, where we also don't just, we kind of sum up all the acoustic features over the entire closing statement or entire opening statement. So that's not the smartest way to do that anyways either. Okay. Yeah, so that would be kind of like a way to do that. Does anybody have any questions?
What made you choose late fusion over early fusion? Like, I just want to know what made you.
That's a good question. So our main reasoning here was that we didn't want to fall into the trap of like this the curse of dimensionality.
Too many features.
Yeah, so we would have maybe too many features. But what we could do, I think, is we could like make an early fusion over maybe like both opening and closing statements of coverall, and then do a classifier there. We could maybe also fuse over all the visual features together and do an early fusion there. This paper was mostly exploratory and like we got into time pressure in the end because we had to record all the, collect all the data, annotate all the data, etc. So we didn't have time to explore everything. But this is kind of like also one of the reasons why I'm offering at the beginning of the class that this data set is available for anybody to use, because there's many things that you could explore. But you could investigate stuff like that in your course project, obviously. Other questions? Okay, so let's look at the results. So what we found is actually pretty awesome. So in the end, these are all the multimodal approaches, because we actually outperform with any multimodal approach all the individual or the unimodal approaches. So I have a different plot in the paper that would show like the unimodal ones come in like somewhere around here. So they're not really bad, but they're also not really outperforming this. So what you see here is in blue the individual performance. So this is how good we are if we classify an individual, and if we're just above you know, like 60%-ish for an individual, then obviously our debate performance will go up already kind of nicely. So the fusion over teams gives you a nice boost there. You can also imagine if you thin slice these opening closing statements into, let's say, like 5-second segments. So you have 5 seconds of this speaker and you have 5 seconds of that speaker and so on, and you try to make an assessment on only 5 seconds of speech, and you were about 52% or 53% correct, so just above chance in a sense that you recognize who is winning by 52 or 53%. If you integrate that over time and you like look at the votes in majority kind of, or like temporal kind of assessment where you have zeros coming in, like you want to see who's winning, but you're 52% of the time correct, then you are very likely to be actually pretty good over the entire debate. So that's kind of cool. But then your question might be a different one. Your question, if you're looking at thin slices, you might want to know, okay, how much time do I need until I know who won, right? So you might only need 30 seconds. You might only need 45 seconds or something like that. So that might be an interesting question there that you could ask. So, but we were not interested in that. We just wanted to explore how well could we detect who is winning. And in the end, we were about 85% of the time correct on a debate level, so we could predict pretty well who is winning. And we only had like 2 or 3 ties that we didn't find a decision for, and then a couple of errors where we made a mistake, just predicted the wrong team to be winning. All right. For future work, yeah, I think there's a lot to be done, and I think there are many options to be explored. But I'd like to leave it there and would like to know if anybody has questions about this. This is the paper, a long title. We thought we were funny. Yeah, so if you have questions, please ask. Otherwise, I would move on to the next paper, which brings a little bit of a different approach to multimodal machine learning, which is also not as much following the ideas and plans that we had during the lecture. Just so you know that there are quite significantly different ways to combine information from different sources in machine learning. So questions?
Why do you use SVM?
Same reason as the other ones. It's just very easy to use, and we had it ready, and it was just the first thing that we wanted to try out. Yeah. It worked quite well, so we stuck with it. Yeah.
For the votes on the debates, do they track from person to person? So if I changed my vote to the for side, and then somebody else changed theirs to the against, would it show that?
Yeah, that's a good question. I don't really know. I also think some speakers actually bring quite a lot of people into the debate, as their friends, or they invite people. And then I've also heard that people strategically vote against the motion or against the wrong way, or the way that they don't think they will vote in the end, and so it wouldn't count as for that team. So yeah, there's always flaws in any kind of data set, so that's a bit of a sad habit. But yeah. Anything else? Okay, let's move on. All right. Okay, so this paper was a collaboration with one of my students, Mathieu, and then Sung-Young Park. He's actually the guy who recorded the data set. Louis-Philippe Morancy is now at CMU. He was Sung-Young's supervisor. and collected the data set together with him while they were still at USC and at ICT. And yeah, so, and actually Louis-Philippe Marcy was the first person to teach that class, and we kind of moved it from a 599 to like actually into the catalog at USC together, and yeah. All right, so as you can see already, like there is something about combining two perspectives. So we try to, in this case, learn from multimodal data in two different types of ways. And the two different types of ways are the following. So in late fusion, you are, in a sense, considering all your modalities to be completely independent of each other. So you learn a classifier only on audio, you learn a classifier only on video, only on text, okay? And they never see data from the other ones, okay? And so, in a sense, that means that you're treating those classifiers in a naive Bayesian way, or where you kind of model them separately, there's no connection between them, and that's the first perspective. The second perspective is if you learn them jointly. So you kind of do the early fusion thing, where you throw in all the data into one feature vector and then learn from the data jointly. So you consider the modalities to be completely dependent on each other. So there's no independence assumption anymore. But that leads to a lot of times like large feature vectors and so on. So we try to do something different here. We try to explicitly enforce those features in all the modalities that are correlated with each other and strengthen those and throw away all the features that are not correlated with each other. So we want to kind of create this this set of features that are super correlated and super dependent on each other and model those plus the independent ones. Okay, so that's that, and we are trying to recognize speaker traits, and the speaker traits that we are interested in. So we use verbal and nonverbal cues. Verbal, so that's text, and we also use visual and acoustic cues as usual. And the two kind of speaker traits that we're interested in are basically pathos and ethos. And so ethos, in a sense, the perceived credibility of the speaker, and pathos, the perceived degree of passion the speaker has, and then you could also imagine like, okay, there should be logos at some point, so the argument, the type of like the persuasiveness of the speaker. But in this case, we are looking at pathos and ethos. We like just as a motivation, we really like the internet. We think it's a great source of information and data, and in particular like YouTube and this Expo TV kind of thing, which is basically like it's an Amazon platform where you can, I guess, buy stuff or just look at video reviews of things like movies and fridges and whatnot, and books. And we want to know if within those kind of like opinion data or videos where somebody expresses an opinion, if we can identify if somebody is credible or passionate about the product that they want to sell or the product that they want to talk about. And in this case, we reduced it to movie reviews, and yeah, we want to both model the independence and intermodality dependencies explicitly to kind of get at these two things. We had 3 research questions, but in the interest of time, I'm only focusing on the first one, which I think is the most interesting one. It's like how to represent features and fuse them from across multiple modalities so that the intermodality variations and dependencies are effectively captured. So we're proposing to look into the ways where on the one side we have the intermodality dependencies modeled, so the modalities are explicitly modeled as dependent, and on the other side where we have them like completely separate in a naive-based word kind of. In related work, well, we've talked about this. Early fusion has been pretty prevalent, but that's sometimes prone to overfitting, and the curse of dimensionality is kind of like a big deal. A solution to this would be dimensionality reduction. For example, principal component analysis is one of those. But principal component analysis, okay, that does only capture like linear dependencies, and it only captures the main sources of variation. But what we really want to model is the dependencies, or the correlations of different modalities. So all modalities are modeled with equal importance, and only linear dependencies are considered. Okay. To continue, there's this thing called canonical correlation analysis that was introduced, and that one is actually pretty exactly what we need. However, so this is similar to a PCA, but it's not exactly following the same principles. It's a bit outside of the course focus, but it models these dependencies between two different views, and most of the time it's used like if you have two views up to the same data, like maybe visual views, and you would, for example, look at texture and shape, or color and shape, or something like that. But we want to use it with different modalities, so we actually use visual, acoustic, and text domains. But also, as proposed here in 2012, it's limited to two modalities, but we have three. And actually, in the visual domain, we could have multiple ones there too. So we could have Okao and facet features, and we could have open face features, and so on. So we want to like blow that up and kind of work in a multi-view fashion. So the first perspective is to assume independence. The color is really bad, I'm so sorry. And model each modality entirely different, with different distributions. And the second one is to extend CCA to more than two modalities. So that's kind of like our approach towards the problem. All right, and then in the end we want to fuse these two. So perspective 1 and perspective 2 kind of build an ensemble of two classifiers that create a decision. Right, our data set, very simple. We have 1,000 reviews from Expert TV. 500 of those reviews are positive, 500 of those are negative. 500, it was easy to find 5-star ratings. Everybody who's excited about something wants to post that. For the negative reviews, we have 1 and 2 stars, and honestly, everything like 3 and below is probably terrible anyways. Video length, we have 350 unique speakers and about 600 unique movie titles. We annotated those through Mechanical Turk on a bunch of these kind of like different speaker traits. We're looking at credibility and passion. We could have looked obviously at all of them, but who wants to do all that work? And again, this data set is also good. On the Likert scale, we also wanted to know, so all of these 10 or whatever passion and credibility speaker traits were annotated on the Likert scale by Mechanical Turkers, and we wanted to know if they are in agreement of each other. And we found that for passion, they are in agreement with the Krippendorf alpha of 0.69, and a little bit better for credibility. So, like, just like we are always interested in like inter-rater agreement or reliability. That's an important part here too. And we had to now split those reviews into like who's credible, who's not credible, and we split it based off of these two thresholds. So everybody who scored below 2.5 went into the low credibility side, and everybody who scored above 5.5 went into the high credibility. What's the problem here?
They're leaving out a bunch of data.
Exactly, so we throw out a third of our data, so that's bad. But yeah, that's just how we do it. And in the end, we end up with 116 high and low passion, and 122 high credibility, and 111 low credibility. What would be a different approach where we don't have to throw out all the data, but we also don't run into like these issues of like we're arbitrarily splitting high and low individuals?
Directly predict the value. Just predict the value.
Very good. So we would do a regression, for example. Okay. Very good. Great. So our approach then, we use these features. You know them. These are the cover-up features. We use text features. I think we took the pre-trained model of Nikolov that was trained on like the Google Wikipedia language model or something like that. This was a while ago. I need to look into the details, but basically we have a model that condenses the words, which is very high dimensional. So like you have a vocabulary of like 1 million words. So you have a 1 million dimensional vector. You condense that down to a 100 dimensional vector, which is very dense in the word space. And then you have those relationships where like words that are similar or happen to be spoken or written in similar contexts end up close to each other. So trains and stations would end up close to each other because they're often used in the same context, but also happy and elated or like excited would happen to be close to each other because they happen to be next to similar words all the time. Okay, so you have kind of these different concepts. You have things in these spaces. You have emotion or sentiment in these spaces as well. So this is kind of like a very cool way to represent language. And we have the visual features, which you see we split up in 3 different feature sets. So in the end, we have kind of like 5 modalities that we want to model. Okay. Yeah, and we extract some like statistical functions like max, min, mean, etc. All right. And this is our approach. So we have the 3 modalities: audio, text, and video. We have perspective 1 up here, which you see these feature sets are modeled separately to create a prediction. So this is our independent view assumption. And perspective 2, where we first do the multi-view CCA, and we do some clustering with a kernel similarity, which is a little bit different from like a Euclidean similarity measure or a distance measure, but we'll get to that when we talk about kernel machines and support vector machines. And then we try to create this ensemble. And the ensemble is actually pretty easy because we just actually need to take the probability or the output probability of this classifier and the output probability of that classifier and create a weighted sum to make a decision. The only thing that we need to find out is like what weights do we use, and we kind of fine tune on that in a validation set. Okay. So this is our model. So this is the first perspective. We have a row parameter here, which is our weight, and then we have the 1 minus row, which is basically the opposite, so that we sum up to 1 in the end for the second perspective. And we want to know the probabilities of having class equals 1, so high credibility or high passion, given an input sample X. Okay? So that's kind of like the ensemble approach that we took here. This is basically how we model the independent assumption, and sorry for going a bit fast, but we're towards the end of the first hour. And then this is the second perspective, where we extend the canonical correlation analysis to a multi-view approach, and we perform then clustering. So in this multi-view space, we create these like clusters, like unsupervised, in this case using some Gaussian mixture models. So we have the number of Gaussian mixtures to be a hyperparameter that we need to tune for as well. And then a new data point comes in, gets projected into that space. It ends in one of those Gaussian mixture models with different like probabilities or posterior probabilities, and we decide based off of like what other data points are in that cluster, what probability this guy has to be of high credibility or low credibility and so on. Okay. The classification then is basically a non-parametric model. This is how this works. So a new data point like this guy ends up in here, and basically all the pluses are in there and only 3 1s, so this has a higher probability to be of class 2, while if it would end up in here, it would have a higher probability to be class 1. Okay, so that's kind of the idea that we follow here. This is on a very high level level of explanation of this. Okay, and then we use some Gaussian kernels for the similarity for the similarity assessment within these clusters, but you can see it as like you calculate the distance to all the data points using Euclidean. We just did it with Gaussians. Okay. The experiments or the results, we did 5-fold cross-validation for both. We evaluate modality-dependent Bayesian classifiers, P1 and P2, as well as the ensembles. And we have some baselines. We use support vector machines with polynomial kernels and some multimodal support vector machines as well. And then we also have just a baseline for majority or as a rough baseline. This is what we find in the end. Our baselines all end up like around like 50-ish or like 55-ish%. You can see this here. The one that worked best was actually the verbal representations, which is kind of interesting. So these are just these high-level verbal relationship, or like following the distributional hypothesis, where similar words end up in a similar location in a like a 100-dimensional space. So this is not non-verbal at all. So this is like everything but the non-verbal. And then the majority baseline is about this, and we outperform the majority baseline in this case by a little bit. So this is all unimodal, okay? So now, if we move to the multimodal, we suddenly see the following. So this is just for baseline support vector machines, these two, and then first perspective, second perspective, and then the ensemble, and we see that we have a slight improvement for passion, and we don't improve on the second perspective on credibility. But as you can see, the baselines are, we jump up there and we significantly outperform the other approaches with all these methods. Unfortunately, obviously, the ensemble didn't bring too much more like performance, but it is a nice boost in this case here, not so much in the credibility. Conclusions, it's kind of exciting to see that these two perspectives help a little bit. They didn't help too much, but I think there's something to be explored there. And yeah, as I mentioned, after pathos and ethos, what about logos? So it's kind of the end of the presentation. Are there questions for that? Otherwise, we can take a short break. Yes?
Because the ensemble wasn't very significantly better than either perspective, do you think there's pretty much the same information by both the perspectives?
That's what I think, yeah. I think that the multi-view CCA was not the best approach for the second perspective. And that assuming entire independence for all the modalities is also the wrong approach. So we kind of try to, I think in both cases where we say we think that all the modalities are completely entirely independent from each other, versus the other one where we say that all completely dependent, that's not the right approach. So I think what we want to do is kind of like find the middle ground, where we learn how the acoustic information relates to the visual domain explicitly from the data, and model that explicitly versus then try to like keep on the side what is independent and use that these two streams to learn.
Like all possible parallel combinations.
Yeah. And so we are actually right now building a neural language model that does exactly that, where we have on the one side, we have a stream of verbal information going in, and then we have acoustic nonverbal information going into the model. But we also have the verbal information going to the acoustic model. And what we try to do there is we try to learn these distributional vectors of words, where through one stream you learn stuff like part of speech, like the stuff that Mathieu was talking about, like verb, noun, pronoun, etc. So this goes in here, but then all the sentiment, all the emotion, these kind of things go into the second stream, which merges with the acoustic model. So you learn this shared space of verbal emotion and acoustic emotion, and then that goes into a language model. So we're exploring that idea right now. Don't put that on the web.
Oh, sorry. No, don't worry.
So that's kind of like the ideas that we're following right now, where we try to, like, not follow these very strict dependent kind of ways, but like find the middle ground. And I think that might be the real improvement or the real benefit there. Okay. Other questions? Let's do let's meet at 9:05, and if maybe the first group can set up already.